Today is a simple question mark exercise predicting the next word. So I'm going to talk about predicting the next word in a sentence. And the reason why we would want to do something like this is, of course, the motivation that I talked about at the very beginning of the class, which is determining whether sentences are grammatical or not. So, we have Jane went to the store to Jane went etc. And I think people are aware of this task from your algorithms for NLP or whatever other NLP class you took. And it is called... Yes. Well, it's called language modeling. So people are familiar with that. You were laughing, so sorry. So it's called language modeling, and in order to do language modeling, we'd like to calculate the probability of the sentence and say whether it's it's a good sentence or a bad sentence. And the way we do this is we define our sentence as X, and using the chain rule, we step through the sentence from start to beginning, and we calculate the probability of the next word, and we multiply them all together. So basically, yeah, that's the next word, and that's the context that we're calculating this based on, calculating the probabilities. So if we can do this, we can judge the how grammatical a sentence is. We can use this in machine translation, speech recognition, whatever other application that you would want to do. And it's it's pretty useful as a task on its own, so a lot of people are interested in it because it's also a very easy way to tell whether you're actually able to model language, or a very direct way to tell whether you're able to model language or not. So then the big problem becomes, how do we predict the probability of the next word? So I'm assuming that everybody knows n-gram language models because the prerequisite for the class was that you took algorithms for NLP, which covered these. But just in case, I will do a very brief review. So the way we calculate the probability in an n-gram language model is we count up the frequency of each sequence and divide. So if we have a sequence of words, the boy ate, and then we have a sequence of words, the boy ate a watermelon, the boy ate and then we have the sequence of words, the boy ate a watermelon, then the probability of watermelon given the boy ate would be the count of the boy ate a watermelon divided by the count of the boy ate And of course, sometimes you're not going to have seen the boy ate a watermelon in your training data. So we do things like smoothing. What smoothing technique did you do in algorithms? Knesser-Nye. So Knesser-Nye smoothing. This is just linear interpolation between the top one and the bottom one, which is a little bit simpler than that. But you need some way of taking a longer context, which is the thing on the top, and combining it together with a shorter context, which is the thing on the bottom. So yeah, modified Knesser-Nye is kind of the ruler of n-gram language models for 20 years or something like this, and it was very hard to beat. But it's also pretty complicated, right? It took non-trivial effort to implement this, and there was a lot of kind of engineering that went into making sure that it worked properly. Okay, so a brief refresher on how we evaluate these models. One way we can evaluate a language model is through log likelihood. This is the probability of, let's say our output is E here, which switched from X in the previous slide. But let's say our output is E. Then we have a test corpus, which is kind of calligraphy E. And to calculate the log likelihood over the test corpus, we add together the log likelihoods of each sentence. Another thing we evaluate is per word log likelihoods. So we have the length of the test sentence, the length of the test corpus, and we divide this log likelihood by the test corpus length. And then we might have something like per word cross entropy, where we further take the negative of the log, and often when we're measuring entropy, we do 2 to calculate the bits of entropy. And then we might also have something like perplexity, where we exponentiate this. And any of these are valid measures. Usually people use perplexity kind of for historical reasons. So there's actually a paper that proposes perplexity as an evaluation measure for language models, or a presentation by a famous researcher named Fred Jelinek. I don't know if you might have heard of him, but he actually did a presentation presenting perplexity as an evaluation measure. So everybody, if you use perplexity, you should cite his presentation. Just kidding. You don't need to do that. Now everybody knows. Okay, so what can we do with LMs? We can score sentences. So Jane went to the store, we'll get a high probability. Store to Jane went the, we'll get a low probability. And this is the same as calculating a loss function for training these language models. So our loss function during training the language model will also be this probability. Another thing that we can do is we can generate sentences. So in order to kind of test qualitatively whether these language models are doing a good job at modeling language, we can generate a whole bunch of sentences from them and see if they look like natural English, I guess. So in order to do this, what we do is, while we didn't choose the end of sentence symbol, so while we're not done generating the sentence, we calculate the probability. We sample a new word from the probability distribution. So this is all review, right? Just to confirm. Okay. So now the next thing I'd like to talk about is a few problems with language models. And this is similar to what I talked about in the first class, which is problems with language that we would like to model. And there are concrete problems with this particular approach. So one particular problem with this approach in the Ngram count-based language modeling framework is that, for example, if we have she bought a car, she purchased a car, she bought a bicycle, she purchased a bicycle. You can see the blue things are basically the same, right? They're basically they're a little bit different in register, maybe. You might say bought in some situations where you don't say purchased, and vice versa. But they basically mean the same thing, so they will probably appear in similar contexts. Similarly, bicycle and car are both vehicles, so they'll also appear in similar contexts, probably. And in algorithms for NLP, I don't think you did class-based language models or anything like this, did you? No? Okay. So class-based language models are a way that people would do this in the Ngram language modeling framework, where you would separate words into classes, so that, for example, bought and purchased would become the same class. Bicycle and car might become the same class. And then you would kind of abstract away, which would allow you to use your data better and generalize more easily. So another problem that Ngram language models, is implemented in the naive way, cannot handle is they cannot condition on context with intervening words. So for example, if we have Dr. something Smith, Dr. something Smith is actually pretty common, right? It's a pretty common pattern that you would see. But if you have Dr. Jane Smith, you might have this in your training corpus somewhere, because there's a Jane Smith on the internet that you've downloaded, and your big data has Jane Smith in it somewhere. But something like Gertrude Smith might not appear in your corpus. And if this is the case, what Ngram language models do is they gradually back off until you get shorter and shorter word sequences, and then you basically lose the context that you were conditioning on previously, and you will not even be able to predict Smith because you've never seen the words Gertrude Smith before. And this is despite the fact that you've seen the doctor, which could be very helpful to you. And a third thing that they cannot do very well. Oh, so sorry. And a solution to this was something called a skipgram language model. I think a lot of people have heard skipgram, maybe in the context of word2vec, but actually the first use of skipgram was basically a type of language model where instead of conditioning on the previous word, you would condition on 2 words ago or something like that. So there is something like this as well. And then the final thing is that they can't handle long distance dependencies very well. So we have something like for tennis class, he wanted to buy his own racket. And for programming class, he wanted to buy his own computer. And if you swap the 2 red words, you get something that's not very, semantically correct, right? Unless you get really frustrated in your programming class. And so there's also solutions to this in the Ngram language modeling framework. There are cache models where you remember words you've already generated. There are trigger models, which basically remember words that, that correspond to each other. So there's a paper that is very interesting to read if you've never seen it before. It's called A Bit of Progress in Language Modeling. And it's by a researcher called Joshua Goodman, who was at Harvard at the time, I believe. And what he did basically was he said, okay, we have all of these solutions to all of these problems with Ngram language models. So I'm going to go in and implement all of them. I'm going to combine all of them together. I'm going to tune their parameters and see how much better we do in language modeling. And this was in like 1997 or something like that. And the conclusion was that he got a bit gain in entropy. So the title is actually a pun. It's a bit of entropy progress in language modeling. And his conclusion from that paper is language modeling is solved. We don't need to do this anymore. We already know how to solve all of our problems in language modeling. But in reality, that's not really the case. And the reason why is because the only person who could implement that was Joshua Goodman. And there was so much engineering that went into that paper that in reality, in real systems, people weren't using any of these techniques and just fell back to our traditional language models. So what can we do about this this engineering burden in our Ngram language modeling framework? And we can take a first attempt, which is featureized log linear language models. First, are there any questions about what I talked about so far? No. Okay. So the alternative, the first alternative we can come up with is featureized log linear language models. So basically the idea here is that instead of conditioning on the context with count-based language models, we calculate the features of the context, and based on these features, we calculate probabilities. And we optimize the feature weights using some sort of method called gradient descent, such as gradient descent, etc. So let's say we have previous words. Let's say arbitrarily we pick giving A is the previous words in our context. And then we have and the and talk and gift and hat. And these are our output vocabulary, basically. These are the things that we could predict over. So then we have our bias vector. This is something that I talked about a little bit last time, but not in very concrete terms. So this time, in more concrete terms, this bias vector might be a score over each word. And it tells us how likely the word is independent of context. So this is the kind of function of a bias vector in a model like this. Then we have another feature, which is how likely is the word given that the previous word is A. So we have a feature vector where we look up this feature vector based on the fact that the previous word was A. Then we have another one that is how likely is the next word given that the previous word, that the second previous word was giving. And this gives us a total score of over all the things in our vocabulary given our context. And as a result, we can see that and the are very likely in general, but given that the previous word is A, they become much less likely because and the are not well-formed English sentences. And then given that the second previous word is giving, giving a talk, giving a gift are more likely than they would be otherwise. So they get a small bonus from this feature. So if we add everything together, we get something like giving a gift being a higher score and giving a talk being a slightly lower score. And I talked about softmax last time. This is something you see pretty frequently, so I think many people in the class might already know this, but just in case. The softmax is basically a way to take in arbitrary scores, arbitrary real-valued numbers, and change them into a probability distribution. So we take in all these scores, we exponentiate all of the scores, which changes them from minus infinity to infinity to to 0 to minus infinity, changes the range. And then we normalize all of them by dividing over the entire vocabulary, which gives us something that sums up to 1. And this is the result. So if we input this score vector into a softmax, we get something like this, with 44% of the probability going to 2.2, the one with score of 2.2, and 32% going to the next one. So as I talked about before, everything in neural network land is a computation graph. So we can also express this, this log linear model as a computation graph. And it's very similar to the one that I talked about last time with the bag of words model. So what we do is we look up giving, we look up A, and this gives us vectors over the vocabulary. We add a bias, we add them all together, we get scores, we take a softmax, and we get probabilities. And the only difference from last time is now instead of our bag of words model where we looked up everything independently, now we're looking up the second to previous word in one basically big parameter matrix, and the previous word in another parameter matrix. Yeah, so a note on lookup. When I say lookup, what this means is basically grabbing a single vector from a big matrix of word embeddings. So if we have the matrix where the number of rows is equal to the vector size and the number of columns is equal to the number of words, lookup 2 would basically be taking the second or third, depending on whether you zero index. Another way to look at this, and understanding both of these is important or useful later, but another way to look at this is you can also view this as multiplying this big matrix by something called a one-hot vector. And the one-hot vector is basically a vector where all of the elements except one are 0, and the one element corresponding to the index that you're interested in looking up is equal to 1. And both of these are identical. Both of these are identical operations from a mathematical point of view. The former tends to be faster. So when this is implemented in a neural network toolkit or whatever you're using, it tends to actually be doing the former, where it just grabs a vector. But this can be more flexible. So you can think of like what happens if I don't set only a single one of these to 1? What if I set multiple ones to 1? What if I set it to something other than 1? And then that allows you to create more flexible models, and I'll be talking about some of those later. So to train this model, we calculate a loss function which is a measure of how bad our predictions are. So basically, if our model is good, it will get a very low loss function. If our model is bad, it will get a very high loss function. And the most common loss function for probabilistic models is the negative log likelihood. So basically what we do is if this third element here is the correct element, we pick that out of the this vector. We take the negative and we take the log, and this gives us our loss. So if our correct element has a probability of 0.329, then our loss will be 1.112, like this. And in some of the DINET code I showed you yesterday, the loss function is called pick neg log softmax. And the reason why is because you pick the value of the negative log after taking the softmax of the scores. So it's unnecessarily verbose way of telling you exactly what it's doing, but that's the reason why it's called that. Okay. And then backpropagation allows us to calculate the derivative of the loss with respect to the parameters. And then a simple stochastic gradient descent optimizes the parameters according to the following rule. So where we take theta and we set theta equal to theta minus alpha, the learning rate, times the loss, the derivative of the loss. Yeah.
For the previous model,
yeah,
we don't really need to do this, right? Like all the vector values can be obtained by just simple counts. Like what's the probability of word given in that context?
Oh, okay. So let me
For that very specific model.
That's a good observation, but actually that's not correct for the case of log linear models. And the reason why is because you're adding these together and taking the softmax after it. So if you did that purely by counts, that would be a naive Bayes model. And a naive Bayes model, compared to a naive Bayes model, this is like a logistic regression model. So that's the difference between a log linear model and the count-based models that we talked about. And actually, the reason why people didn't use these was because these were too hard to train on the hardware that people had at the time. So if these had been as easy to train as neural networks are now, maybe everybody would have been using these instead of n-gram language models. Okay, so I have a code example of how you implement something like this, just for completeness. But before that, there's a few things that you need to think about when you're using neural models for NLP. And one that is very important and is especially important when you're doing stuff like predicting the probability of a word is choosing your vocabulary. So you will always have unknown words, which are basically words that appear in your test data but do not appear in your training data. So yeah, we don't have all the words in our world in our training data. But on the other hand, if you make an infinitely, or if you use all of the words in your training data in your neural network model, larger vocabularies generally require more memory and more computation time. So the reason why they require more memory is because the big matrix containing all of your parameters for each word gets larger. The reason why they require more computation time is because things like this softmax here function over the entire vocabulary. Things like adding up the parameters here also function over the entire vocabulary. So if your vocabulary gets larger, the time increases linearly. So what we need to do, what we normally do in neural network models, is choose a smaller vocabulary than all the words in our training corpus. One common way to do it is to to change all singletons into the special unknown word token. So all words where the frequency is less than or equal to 1, you change them into an unknown word token. Another way to do this is through a rank threshold. So you say, I'm going to take the top 10,000. I'm going to take the top 10,000 words, and everything else is going to be unknown. Recently, there's been a move towards using kind of models of subwords or models of characters, which I'll also talk about later. But assuming we want to use words themselves, these are common methods to do so. One point is that when you're evaluating these language models, it's really important that the vocabulary must be the same over all your models you compare, or at least all of the models that you compare have the ability to generate all of the vocabulary in the training corpus. So, like an example of this is if you have a test set and you can generate all the words in the test set, it doesn't matter whether you use a word-based model or a character-based model. The character-based model might be able to generate more words than the word-based model is, but as long as the word-based model is able to generate everything in the test set, it's okay to compare between them. But in general, you are comparing word-based models with word-based models, so then you just need to make the vocabulary the same. Yeah.
Doesn't that mean that you have to effectively know the content of the test set? So would it be fair to compare models that can basically generate the same chunk of the test set? So as long as the vocabularies are...
So basically, effectively what you do when you have unknown words in your training data is you make all the words that were unknown in the training data also unknown in the test data. For the purpose of evaluation only. And when you do that, that means that you have like A, B, C, D, E, B, C, D, E, F in your training data. You replace all the singleton words with the UNC symbol. And then when you get B, C, G in the test set, you're essentially also replacing this with the unknown word symbol. So this means that you now have effectively no unknown words in the test set, so you can evaluate over it. And the problem would be if you had another model that also had G. If you had another model that also had G included in it, then you ask this model to generate G instead of UNC. That would be comparing apples to oranges, because UNC is actually easy to generate because it's very common. So you would be unfair to this model that you were asking to generate G. Oh, sorry, I'll try to do that for the class. So the question was, don't you have to effectively know the test set beforehand in order to ensure that your model can generate the entirety of the test set? And the answer is basically, you pre-process the test set in a way that the comparison is fair. For the sake of comparison, you do that. Are there any other questions? No? Okay. Yeah, so this is a little bit confusing, but if you compare a character-based model to a word-based model, where the character-based model only has to generate the same vocabulary as the word-based model, that's okay. But if you're comparing a word-based model to a character-based model where the character-based model has to generate all of the words and the word-based model is allowed to generate UNC sometimes, then that's not fair. Okay, so I have an example of this in code. It's actually really simple, right here. And I would like to talk a little bit about the data set that we use for this. So One thing to be aware of is there are some very standard data sets in the community that people use for evaluating neural models of various sorts. And this is a very famous one called the Penn Tree Bank process by Tomas Mikolov. So it's a version of the Penn Tree Bank data, which is originally created as a tree from the Wall Street Journal. But it's been pre-processed, and the way it's been pre-processed is we have all the unknown words are replaced by UNC, so it only has the top 10,000 words included as in its vocabulary, and all the numbers are replaced by N, by capital N, and it's lowercase. So this is a data set that a lot of people use. And the reason why it's important to consider the data set is I'm actually not going to worry about processing unknown words on my own because they're already processed for me. But if you are using your own data set, you will need to worry about processing unknown words. Okay, so the way this looks in code is a lot of this stuff up here. This is just boilerplate that I used last time to read in corpora and stuff like that. So I think you've seen that. We have the length of the n-gram model, and we have the length of the n-gram. So this would be the previous 2 words we're using. We do stuff like reading in the data and defining our model. And then after we do this, basically we define a word embeddings, or things to look up for the words, where the size of the matrix is the number of words times the number of words. That's because we need to have a full vector the size of the vocabulary for each word that we're using in our context. And we have one of these, the length of the n-gram context that we're using, so we have 2 of these. Then we have our bias vector. Then given our words in our sentence, we get our bias. We create our bias vector, and then for each word in our set of previous words, we look up that word ID in the appropriate parameter set. So we'll look up the first word in the first parameter set, the second word in the second parameter set. Then we sum all of these together, and that's how we calculate the score for a single history. And then to calculate the score for multiple words in the output, what we do is basically we append start of sentence symbols to the beginning of the history, and then we step through each word. We calculate its score. We calculate the softmax, and then we update the history by adding this word to the history. And then in the end, we can sum up all the losses. So basically what we're doing is we're stepping through, we're stepping through this process here for all of the words in our sentence. And if we do this, we can calculate the loss. So as I mentioned last time, if we can calculate the loss, we can train our model. So now we can basically reuse our model training code from what we had last time. But one more kind of interesting thing that we can do is we can generate sentences. So we look up, what we do is we seed our history with start of sentence symbols, and then while true, so we continue until we're done generating. We calculate the probability, or we calculate the score. We calculate the probability through the softmax, and we get a NumPy array of this. Then we randomly choose from this. Probability distribution the next word, and if the next word is the end of sentence symbol, or we've reached a maximum length, then we terminate and we output the sentence. The reason why we have the max length thing here is these things tend to get stuck and generate forever if you don't do this, and it's good to not have infinite loops in your programs. This is very common to do for sequence models or anything else. So then the training loop's the same, and then you can generate things. Yeah, the code is available on the website. So if you want to download this and play with this, you can. I won't run it here because my computer might overheat. So yeah.
I'm curious why you're using the random choice as opposed to picking the thing with the maximum probability.
Oh, that's a good point. I'm going to talk about that at some point, but there's two ways to generate. One is to take the maximum, and one is to randomly sample, and they both have different use cases. Randomly sampling is good for language models because the language models aren't conditioned on anything, which means if you take the max, you'll get the same thing every time. So randomly sampling is a more interesting way of getting outputs because you don't just want to know the number one sentence. Yeah, I'll talk about this in more detail. There's like applications like dialogue where you want a little bit of variety. You might want to sample, while things like machine translation, you might want to take the max. Yeah.
You have different implementation for lookup 1 and lookup 2.
Yeah, these are different. That might not have been immediately clear, but we're defining a number of lookups equal to the size of the context. Yeah.
Just a small thing. What is this need of without sum? Isn't it already on after the soft ones? So when you're essentially choosing the next random word in the same distribution.
Oh yeah. This is an artifact of NumPy being very picky about your thing summing to exactly 1 and not 1.0000001. So, yeah. Okay, so this is an example of a log linear model. I will now move on to onto neural networks, which are the point of this class. And oh, by the way, has anyone taken language and statistics? Yeah. So these models were basically invented by Roni Rosenfeld. So, a bit of CMU related trivia. Okay. So I talked about before problems with n-gram language models. So the n-gram language models had several problems, 3 of which are noted here. So the fact that they could not share strength among similar words, the n-gram language models could not share strength among similar words. This is still a problem. The reason why it's still a problem is because basically we have this big matrix of the number of words by the number of words, and we need to learn parameters for all of these. And there's no concept of word similarity within that matrix because it's a full rank matrix that we have to learn every parameter for. On the other hand, this problem of not being able to condition on context with intervening words, this is solved now. And the reason why it's solved is we have a direct connection between 2 words ago and the current word. And so, for example, if we have in our lookup 2 words ago, Dr. this word Smith, this is something that we can express in this mode. In long-term dependencies, obviously, these are not solved yet either because we're still conditioning on a limited context. So this motivates an expansion to nonlinear models. Another reason why is because linear models can't learn feature combinations in a trivial way. So let's say we have farmers eat steak. This is a pretty high probability sequence. Cows eat steak is a pretty low probability sequence, hopefully. Farmers eat hay is a low probability sequence maybe, and cows eat hay is higher probability. So you can see that there's an interaction between not just farmers and steak, two positions apart, but actually it has to be farmers eat and steak, and cows and eat and steak, etc. So these cannot be expressed by linear features trivially. So what can we do here? And one thing that we can do, and one thing that people tried to do when these linear models were all we could use, was remember the combinations as features. So remembering farmers eat, cows eat. And the obvious problem with this is that the feature space explodes. Before we had the number of words times the number of words times the n-gram length that we were considering. Now suddenly it becomes number of words times number of words times number of words, and we need to remember all of these features, and this becomes easily intractable. And the other way is to use neural nets, and as I mentioned last time, neural nets are a way to learn feature combinations, to do good feature combination. So the first attempt at a neural language model, what we can do is basically what we do is exactly the same thing as a log linear language model, but we just put some neural network layers in. And it's pretty simple. What we do is we look up. So now we have two vectors. And we run these two vectors through a neural network layer, a tan-h multiplied by weights and plus a bias. And now we get a new purple vector, and our purple vectors are feature combination vectors. These are the vectors that learn to combine things. Yeah. Yeah. Uh-huh. So the question was, where are feature combinations important that skipgrams cannot be used to solve? And basically, I think my previous example is actually a pretty good example of that. So a skipgram might be able to handle farmers eat. Might be able to handle the fact that farmers and steak tend to co-occur two words apart from each other, but it couldn't consider the fact that farmers eat hay is bad, but farmers grow hay is good. So actually that would have been a better example. So farmers eat hay and farmers grow hay. You really need to know that it's not just that you had farmers 2 times ago, but you actually need to know all 3 words to modify this. Probability. Okay. So yeah, let's go back to this. So now we have our combination. Oh, yeah.
So what was the use just a larger size of the n-gram for the previous case?
So the reason why the larger size of the n-gram doesn't work for the previous case is captured in my second point here. So you can see they cannot condition on the context when we have an intervening word that we haven't seen before. So if you make the context longer, you get more likely to have these in things that you've never seen, I guess. Any other questions? No? Okay. So neural language models, now we have our combination features. Neural networks extract these combination features very well. So then we do an additional matrix multiply, add a bias, and get scores for all of the words. So now what we're doing is instead of directly calculating the probability of the scores of each of the words, we're extracting word embeddings here. And we are transforming these word embeddings to extract combination features. Then based on these features, we're deciding the probability of the next word in the sequence. And then, of course, we take the softmax to get the probability. So I think to understand this intuitively, the best point of this is kind of twofold. We can extract combination features, and we can also share strength among similar contexts or similar words in the output. And these things are word embeddings here. These word embeddings will always be giving the same red vector to this word giving. And similar input words will get similar vectors. So if we have our example, or do I have a, sorry. Yeah, I don't have a concrete example. So purchased and bought will probably get similar vectors in this model. Because if they do, they'll be able to do the language modeling task more accurately. So because of that, the red vectors will be more similar if the words are more similar, syntactically or semantically or whatever. On the other hand, the softmax here, this word, this matrix of softmax parameters basically will be similar for words that appear in similar contexts. So if we have two words that we need to be predicting similarly in similar contexts, also probably purchased and bought will appear in similar contexts. Cow and cattle will appear in similar contexts. And for this weight matrix here, the entries of the weight matrix corresponding to the words will be similar. And finally, similar contexts will get similar hidden states. So our neural network feature extractor will try to make these purple vectors here similar if the context is similar, and the words that will come next will be similar. So if we look at this, now what problems are handled? Now we can share strength among similar words, and we can we don't only share strength among similar words, we also share strength among similar contexts as well. So this is very useful. We can, of course, condition on context with intervening words like we were able to for previous ones. Or actually, I shouldn't say of course, but basically, we're looking at two words before by looking up giving in this case. And a few of our features in this purple vector here will probably just ignore the word A. So we'll probably have a few features extracted in this vector that ignore the intervening word. So this could also help us condition. And the final problem we still cannot solve yet, but we will be able to solve very soon. Yeah.
Then also there are these word embeddings.
Uh-huh.
In the previous model you showed, right?
Yes.
Then also there are these kind of word embeddings.
Mm-hmm.
So wouldn't that first problem should be solved there also? See the words.
Oh yeah. So it is solved in this model. So the first two are solved, and then the last one is not solved.
No, I mean the previous model where you didn't have.
Oh, okay. So that's a good point, and maybe illustrates the. I should illustrate the difference between these, but basically, these red vectors here, these are going to be like 128 dimensional. They're going to be small, relatively small, 256 maybe. In contrast, in the previous model that I showed, each vector for each word was the size of the vocabulary. So what it's basically saying is, given that this word occurred, what is the probability of another word? And because of that, the 128 dimensional kind of like low dimensional things that we use here are much more generalizable than memorizing the next word for each one. There. Yeah. Does that make sense? Okay. Cool. So any other questions? Yeah.
If you could go, pop back to the diagram.
Sure.
I'm a little bit confused by the notation. So you've got tan H, W, and so on, and then you've got a W beneath it as well. Are those the same?
No, they're different W's. I'm sorry. I should subscript this as well as like the weight matrix for the softmax. So it would be like W, SM, or something like that, which is I think what I use in my code. Yeah. Yeah.
So are you training the parameters with the likelihood that these two words would occur together?
You're training the parameters with the negative log likelihood based on this probability vector. So this probability vector is the probability of the next word, but during training you actually know the next word, right? So you select, let's say word number 4 was the correct one. You select that negative log, and that's your loss function. And then because it's a neural network, your loss function gets backpropagated all the way back through all of the parameters of the model. You update all of it. These word embeddings,
So essentially taking the word embeddings for the next word.
so you're training all of the parameters of the model, including the word embeddings here, and this and this. And actually, the word embedding, or word embeddings were existed long before word2vec, and actually this particular model by Yasuo Bengio was kind of one of the first models to use word embeddings like this in a neural network type style model. So they originally were made by this, and what word2vec did was basically it made it training really fast. So, but word embeddings don't have to be word2vec or pre-initialized ones. Yeah.
I guess I'm confused how these embeddings get trained.
Mm-hmm.
Because you can take the derivative, obviously, but tan H and
Mm-hmm.
that down
Yep.
to the lookup layer, but then how do you differentiate that lookup layer with respect to here?
Okay, so that's a good question. So if you go all the way back to this, you'll see that a lookup layer is actually just a vector multiply. You're multiplying a one-hot vector. So essentially, if you get a gradient back from this here, it will be multiplied by this vector, and that vector multiplication can also be differentiated, which means you can backprop all the way into this matrix. But for practical purposes, because updating this whole matrix every time would be slow, what you often do is you just update the particular vector, the gradient itself. Yeah.
Benefit does weighting and biasing the softmax instead of directly doing a nonlinear transformation and providing those?
So what would be the alternative to multiplying by weights and biasing?
So if we were directly taking nonlinear transformation of tan H and providing it to softmax as whatever the nonlinear transformations to provide to indirect softmax.
So that's an interesting question. Yeah, let me go back to the diagram. So I guess no, I need to go forward to the diagram. So I guess the question would be, what is the benefit of doing this, multiplying this, instead of directly using the output of this? So directly using the output of this and taking the softmax wouldn't work at all. And the reason why it wouldn't work at all, and this is a really common mistake that people make when implementing neural network models, is you should not be taking a tan H or any nonlinearity before you take the softmax. And the reason why is because that limits the range of probabilities that you can calculate. Then the second question would be, okay, let's say we forgot the tan H and just took the softmax directly. That would be exactly the log linear model that I talked about before. So, yeah.
Is that just a kind of mapping from the entire open space to the
you can think of a word embedding. So what is a word embedding? What does a word embedding mean? A word embedding is a mapping from a word into a continuous vector. Yeah, continuous vector. Okay, so I will continue. And so I'll do this really quickly because we're a little bit short on time. But basically, when you change the log linear model into a neural network model, all you need to do is you need to specify your embedding size and your hidden size, and you add a weight matrix for your nonlinear transform, and then you have a separate weight matrix for the softmax, which is what you asked before, and then we do a nonlinear transform, and then we do our affine transform to get the output. So it's very, very similar to the log linear model that I talked about before, but we're just adding a word embedding lookup and a nonlinear layer. And then everything else is I think, exactly the same. Okay, so now I will go next to the next thing. So this is one point. One thing that you can actually do is you can share the embeddings between the input and the output. What this means is basically this softmax is a big matrix where the length is equal to the number of rows is equal to the number of words in the vocabulary, and the number of columns is equal to the size of this hidden layer. If you set the size of the hidden layer equal to the size of your word embeddings, you can actually share the parameters of these two matrices. And by doing this, basically, because a large portion of the parameters in your neural network model are in this lookup and this softmax, this reduces the parameters in your model by approximately half and can help your generalization. And this is a pretty standard thing to do now. I think a lot of people do this. If you want a small challenge to try this, you can download the sample code and try to do this yourself.
Is there any advantage of sharing these parameters apart from like just reducing the parameters? Performance gains.
Well, so you reduce the parameters and you reduce the number of parameters and you basically double the learning opportunities for the parameters, if you see what I mean. So each parameter, if you had one lookup and one softmax here, they would participate in twice as many training examples. So.
Like practice doesn't help improve accuracy, or
Yes, it does. Yeah.
This may be going too deep, but how would you do an update of the weights if you're sharing?
So in the softmax, you have to do the update of the weights of all the weights anyway. So you just basically this is the same as always, and then this one you'll be back propagating through basically a pick row operation, which is like a lookup operation, I guess. Okay, so I'd like to talk about a few training tricks. There will be, I guess, lots of training tricks in this class, but training tricks are actually quite important. So I will, I'll spend some time talking about them. The first one that I mentioned very briefly last time is that you should be shuffling your training data. I guess not training tricks. These are training, I guess, best practices that you should be following most of the time, and most people who implement these models follow. Number one is that you need to be shuffling your training data. So every time, either once before training or ideally every time before you make a pass through your training data, randomly shuffle the order of it. The reason why is stochastic gradient methods update the parameters a little bit at a time. So if you think, what if we have a sentence, I love this sentence so much at the end of the training data 50 times? What will happen is it will update to improve the probability of I love this sentence so much, and it will do it 50 times in a row, which means you will get a language model that can only generate I love this sentence so much. This is kind of a made-up example, but you can think of plenty of examples where you concatenate two training corpora together, and they have different features. So the second corpus dominates the training. Yeah, so to train correctly according to stochastic gradient descent by theory, you should be shuffling it at every time step, but in reality, usually people just shuffle at the beginning of each epoch or pass through the training data. Another thing is that there's a lot of options for optimizers. So I talked about the stochastic gradient descent method, where you basically add the derivatives of the parameters. There's a bunch of other optimizers, and there's a very good summary of optimizers if you want to read more. And it's, I believe, cited on the website. But just to run through a few of them very quickly. So there's SGD with momentum, which basically remembers the updates that you've done previously and continues updating in that direction. There's also Adigrad, which is a method that learns an individual learning rate for each parameter that you have in your training data. And the idea is that parameters that are more frequently updated, you don't want to update them quite as much. And parameters that aren't updated very frequently, you want to update them more to ensure that they're learned well. And then ADAM is kind of the de facto standard that a lot of people use now. It's like Adigrad, but it also keeps a running average of the momentum and the gradient variance and does appropriate adjustments there. There's tons of others, RMS prop, Ada delta. I think a lot of people have kind of stabilized on using ADAM as the default, but every once in a while you see people using other ones. There's also an interesting paper which I forgot to add to the this list here, but it might be worth taking a look at it. NIPS this year, which basically shows that stochastic gradient descent takes longer to converge, but often converges to a better place than these other ones. So these other kind of adaptive methods like Adigrad and ADAM, et cetera, tend to overfit more easily than regular stochastic gradient descent. So it's important to know that they sometimes overfit. And I think this is something that a lot of people kind of knew if you use neural networks a lot, but now this paper came out, so you can actually read about it in detail. Yeah, I will add that to the references. Two other tricks for optimizing your model. One is early stopping, one is learning rate decay. So neural networks have tons of parameters. They have many, many parameters. And we want to prevent them from overfitting. We want to prevent them from learning the training data only and not generalizing to the development data. A very standard way to do this that you should be doing is you monitor the held out development, the performance on the held out development data, and stop training when it starts to get worse. So in other words, once you start overfitting, you just stop training and you save your model. You use the model that worked the best out of all the ones you've tried. Another thing that sometimes helps is when you start getting worse, you reduce the learning rate and continue training. This is also very, very common. So once your development accuracy starts to get worse, you cut the learning rate in half and then continue training from there. And smaller learning rates are harder to overfit because they tend to not be pulled in the direction of individual examples quite as much. So this is also very effective. Yeah, so which one to use? ADAM is usually fast to converge and stable. SGD tends to do well in terms of generalization. You should definitely use learning rate decay. This is a paper by me and Michael Denkowski at Amazon. We tried this for machine translation tasks, and Atom with learning rate decay seems to work pretty well. But other people have other conclusions. So I guess the moral of the story is Atom is a pretty good initial choice. You could also try SGD and see which one works better. So dropout. This is another way to prevent overfitting that you probably hear about relatively frequently if you read neural network papers. And so the way this works is by randomly zeroing out nodes in the hidden layer with probability p. And you do this at training time only. So at test time, you do not do this. So what this looks like is if we have our nice vector, feature vector of extracted parameters, we basically zero out some of them. We set some of them to 0, and we keep the other ones the same. And the reason why this is effective is it basically makes it much more difficult for the model to memorize the data in a consistent way. And because you're randomly dropping out things, this adds more noise during the training process and makes it more difficult to do this. And if you go into the theory, basically what this is doing is this is learning an exponential number of models and then combining them all together at the end. But you can also just think of it as if you don't want to worry about that, you can think of it as a way to regularize your models. Almost all neural network toolkits have some sort of dropout function that you can use. So this is something that you just apply, and then you set the dropout rate. You can set it to 0.5, which is kind of a theoretically good value. But generally, the larger you set it, the stronger the regularization. Yeah, and you have to do some scaling at test time if you use this. But I'll skip this in the interest of time. And I'll skip this, but you can take a look. This is basically a neural network language model with lots of optimization tricks, or lots of tricks to optimize accuracy. Okay. Any questions? Yeah.
To drop out, increase your conversion time significantly?
Yes, it will increase the amount of time it takes to converge. So the question was, does dropout increase your convergence time? And I think in general, adding regularization of any kind will increase your convergence time. Anything else? Yeah.
Do you also use dropout for embedding layers?
Do you also use dropout for embedding layers? Maybe, depending on whether it improves your performance. But I think the answer is yes. It's pretty frequent to do that. But if you're using pre-trained embeddings, in fixing them and not learning them, it's probably a bad idea. So if you're learning the embeddings along with the model, it's very frequent to do that. But if you're fixing them, then no. Anything else? No. Okay. So the final one. This is pretty important because neural network models take a long time to train. And you don't want to be waiting forever for your experiments to finish. So there's an efficiency trick called mini batching. And the idea behind mini batching is basically on modern hardware, especially GPUs, but also some CPUs, doing many big operations doing a single big operation is faster than doing a for loop over many small operations. The idea behind mini batching for the purpose of efficiency is taking advantage of this fact. So an example of this is if you take 16 additions on a modern CPU, and you run all 16 additions in a for loop, this will take a fair amount of time because you have the overhead of doing the for loop, etc. But if you arrange the additions into consecutive pieces of memory, there's a thing called single instruction multiple data operations, SIMD operations, where basically you can do 16 additions or 32 or 8, depending on your processor, in a single operation. So this removes the for loop overhead, et cetera. Things are even better on GPU, where you have a whole bunch of threads running at the same time. So you might even be able to do 256 in the same time that you could do one. So the idea behind this is basically, let's say we have 3 training examples. One training example has vector x1, one has vector x2, and one has vector x3. What we would normally do is we would multiply each of these vectors by the parameters, by the parameter matrix, add the bias vector, and take a tan H. But what we do instead is basically we concatenate all of these vectors together, and we do a single matrix multiply. We do a thing called broadcasting, which basically kind of duplicates this B along over multiple columns, and then we add that in, and then we take the tan H. And we can, so instead of doing all of these operations independently, we do these together. So the way you can do this manually is basically what you do is you group together similar operations. In the case of our neural network language model, all of our loss calculations for each word are similar operations. So we're doing, for each word, we look up the vectors of the previous 2 words, we run them through a neural network layer, we take a softmax, et cetera. And all of these operations are the same size and everything. This becomes more complicated for recurrent neural networks, which I'll be talking about next time, and I'll be talking about how we mini batch recurrent neural networks next time. How mini batching works depends on the toolkit. I guess most toolkits, what they do is basically they require you to add an extra dimension to your array. Usually it's the first dimension if you're doing something that's based on NumPy. There are lots of examples of this on the internet. I should mention that DINET is a little bit different. Basically, DINET doesn't require you to add the extra dimension and just manages it for you automatically. So I'll give an example of how you do this. And basically what you want to do is we go down and we have not calculate the score of the history, but we have calculate the score of multiple histories. So now we want to calculate the score of multiple words at the same time. So our input for this is a list of histories. So it might be like, let's say we have the sentence. Let's say we have a sentence. He ate it. So our multiple histories would basically be the 2 sentence beginning symbols, the sentence beginning then he ate it, and then we don't need to calculate this one because it's never used as a history. So we have a big list of these, and we then kind of transpose them. So what happens is now we have a list of the IDs for the first words, he ate, and a list of the IDs for the second words. And then we can look up all of these IDs at the same time using this lookup batch function. There's a similar thing in other toolkits. This is the way you do it in DINET. And then all the other stuff is just the same. You just do matrix multiplies, et cetera. So you look up things, and then when you calculate the loss function, similarly, instead of calculating the loss function over a single ID, you calculate the loss function over all of these. He ate it simultaneously. So kind of the idea is before running your processing, you convert everything into a format where your things are synchronized, and this allows you to run everything at the same time. Run all the lookups for this at the same time, run all the lookups for this at the same time, and then calculate that all at the same time also. So I think this is maybe too brief to fully understand, but you can always go back and look at the code after the class if you. It's also possible to do automatic mini batching. So basically, what this is a. The idea behind this is instead of doing mini batching yourself, you just create a graph of the things that you want to, all the operations that you want to execute, and the framework itself will automatically go in and batch things together for you. And there's a couple implementations of this. There's TensorFlow Fold, which basically it does this, but in order to use it efficiently, you kind of need to use special operations. And then the Dynet auto batching, the way it works is you write a for loop over the things that you want to process, and then you turn on a command line option, and it automatically finds things for you. And I should basically, I don't have a lot of time, so I won't go into it in detail, but the automatic batching will be slower than manual batching. The reason why automatic batching is slower than manual batching is because the framework every time has to figure out what to batch together, while you can think about it in your head and come up with that kind of ideal batching strategy. But automatic batching is less overhead to implement, and you can kind of implement things like tree-structured networks, which are very hard to implement in other ways. So I would talk about this in a little bit more detail, but the class is ending now, so I will I'll stop the class is over. So if you have any questions, I'll answer them directly afterwards. Thank you.